Well, looks like we're there. Welcome back, everyone. So we're on our last three classes pretty much, except aside from the final. We're on section 12.3, example 2, but that means we're in the last example of the last section, so we're pretty much just about done with the course. After we complete 12.3, which shouldn't take too long, we'll move over to this document here, Review of Inferential Statistical Methods. Then, after completing that one, with the remaining time reviewing for the course, we'll go to these problems here. But there's always a standing offer if you see an interesting statistical problem, either from WebAssign, a quiz problem, old exam problem, or just something out of the book or elsewhere that you'd like to bring to class. I'll always be happy to take a look at those as a class as well when we're reviewing. Otherwise, we'll stick to these documents here. And pretty much that's my announcements for today. There's not a whole lot to indicate other than definitely the final exam is coming up. It's going to be Monday, December 11th, like we mentioned. 8 to 10 p.m. in this classroom. And the new things are 2 pages of notes will be allowed on this exam, front and back with anything you like on it. And so this is a good opportunity to go and take out your other pages of notes that you've written out for exam 1, 2, and 3, and start consolidating them down together along with the new information. For this final exam, this is going to be a comprehensive exam going all the way up to section 12.2. And thanks for mentioning that about 12.3. Took a look at my notes at home. I did in fact say we're covering 12.3 for the sake of helping out with WebAssign as well. It's just too short of a turnaround, not even an opportunity to do a quiz on it to make it a good problem on the final exam. So as far as chapter 12 goes, expect a confidence interval problem. That's probably going to be a dead giveaway of what is going to be on the exam for chapter 12 rather. Well, any questions or comments at the moment, folks? Okay. Back to the actual Moodle website. A couple other things I want to mention are there's still a couple extra credit opportunities floating around. If you scroll through the Moodle website, they're in various locations. This one is always a standing assumption. And I do this in a lot of my classes. The idea behind this is if you had a bad exam score, but you studied hard on the final exam and learned those topics and made up the credit, your score should reflect that. So your final exam score, only if it's higher then the minimum amongst exams 1, 2, and 3 will replace that minimum score. Say, for example, if the final you got a 90 on it, exam 1 you got a 60, your final stays a 90 and your exam 1 would convert to a 90 instead of a 60. And this only improves your grade, so there's no way for this to actually make your grade go down. Other opportunities are, let's take a look. The course evaluation opportunity. This one's not as exciting, admittedly, since people are doing pretty well in quizzes, and dropping an additional quiz grade might not be the most interesting thing in the world. But if we scroll up, there is this one still floating around. This one is the extra credit quiz. It is a little bit more challenging. It's concepts out of the book, but they are topics we have not covered at all. This one does have a final due date. It'll be on the day of the exam, Monday, December 11th. I'll grade all of those along with the exam. And if you've opened that one up, it looks pretty bad, right? There's like a wall of text of different formulas. But the more you focus on it and look at the parts A, B through E, really, you're not doing anything too different at all. There's a different standard error formula. It looks gnarly, but if you work at this step by step, it's not too hard to put together. Critical number is identical. And what goes here is just the difference of the 2 sample proportions of successes in this problem. So if you decide to tack on this quiz, this is what it's worth, up to 4% extra credit on the final exam, but your final exam score cannot exceed 100% itself with that as a standing assumption. So the purpose of this quiz is if you give it a try, even if you don't nail it perfectly, you'll probably get some of the extra credit here. And that could cover the bases of, say, on the final exam, if I made a simple mistake here or there, this could cover that base. So that's the purpose of this exam. And again, it's going to be due December 11th, the day we take the final exam. Last day for WebAssign itself will be December 12th. That was a lot of announcements. Any questions, folks, so far? Okay, well, let's go back to section 12.3, and then we'll just go down the line of these review topics here. We should also remind ourselves, what did we do in section 12.3? Well, in example 2, we were looking at acidic rain. We're told a lake is going to be considered non-acidic if its pH is greater than 6. So we observed the statistics in the problem, the critical value alpha, And these were the hypotheses we tested. We want to know if the average value for all these high mountain lakes, that's the mu here, is different from a value of 6.5. So right where they put different from here, that indicated the two-tailed test. Then we ran through the formulas, found the degrees of freedom is 14. The standard error came as 1.730. The last thing we calculated was the test statistic. This was kind of the pivotal step on part E, where we're putting a lot of things in together. We looked up our sample mean at 6.60. 6.35 comes from the null hypothesis, and we just threw in our standard error value there. What's next on the table is we have to calculate our p-value. And this one is a little bit more challenging because if that not equals, it means we're dealing with a two-tailed test. Any questions at all, folks, before we go for that p-value down here? Okay, let's sketch the graph and get started on this thing. Probably need a little bit more space than I put in. So the thing to observe with our test statistic is it came out positive. So when we go to draw a graph to organize our thoughts, first thing we'll put is df is 14, just as a reminder. 0 will go here, and t, it's not too far away. It's at about 1.14, maybe around this location. So here's where T star goes, 1.4451. So we'll get all that area there. But if it's a two-tailed test, there's a second set of area we pick up. Right in this location, that's not our, hang on. I put T star there. That's not the best thing to put. It's a little bit of a distraction. Usually T star is for a confidence interval. We should keep it just a T. Not sure why I was thinking a T star on that. That's a small comment, but it's definitely something you wouldn't want to mix up with a confidence interval. So there's the the test statistic T, not T star. And this location is negative 1.4451. We get this area as well. And both sets of area are going to give us our p-value. So here's how we're going to focus on it. We're going to take this and double it. So double this area. So our probability statement is p-value equals, here's the doubling factor, so 2 times. We want the probability that the test statistic t is greater than the value we just found, 1.4451. And so on paper, I'd probably do it this way, just to be careful. It's honestly kind of easy to forget that we have to double the p-value. But if you put this down on paper, this is a really good reminder, especially if you have a highlighter. So now, next thing to put down for information is, this is only the second p-value we've calculated in this particular context. So the reminder is we're using TCDF. So now back in the calculator, we'll hit second bars to start. Go down to option number 6, or just click on 6 for TCDF. And now our lower value, we take a look at the diagram, is going to be 1.4451. I know I honestly forgot. I usually like to indicate that right here in the notes. So this is lower, input number 1. Input number 2 is going to be 10 to the power of 99. Since we're doubling this area, we're going to the right forever. So in the calculator, let's put in 10 power 99. And degrees of freedom is 14. So that's what it should look like. After hitting enter, our p-value came out as a 0.0852. Rounded to 4 decimal places, 0.08. I'll keep a couple extra digits, 199, because I did notice I misspoke when I said that. I said the p-value is 0.0852199 and so on. It's not quite right. That's the p-value before we doubled it. We still have to multiply that thing by 2. So in the calculator, just hit times, give it a factor of 2. And that right there is finally our actual p-value. This one will round to the 4 decimal places. It's a 0.1704. And that step is so easy to miss. I misspoke and said that's our p-value here before doubling it. Let's emphasize it even more. Let's throw a screenshot of the calculator just as a reminder. So when you're doubling the area, this is what we need to do. Don't forget to double this value. Then if we do that, we're in great shape. We've got a p-value. Now we have to do the interesting task of deciding, is that p-value big or is that p-value small? Any volunteers for that question there? Exactly. And that's the best way to say it. It's almost a trick question, right? I can't tell if this is large or small until you go look up the significance level alpha, and that's what we compare it against. So let me take that. One thing I did forget to do, even though it's not a big deal, it's helpful to have it right by our hypotheses. That's a good line to look at a lot of information. So let me carry it down here. Now for the last part of the problem, we're usually just carrying this down. Let's just park it there for the moment. Our significance level was at 0.05. And so we'll come up here. And here's just a really fast comment. Since the p-value came out as a 0.1704, which is bigger than the 0.05 from down here, which is alpha, in this problem, it implies we will fail to reject H naught, the null hypothesis. So like you said, relative to alpha, this p-value is enormous. We don't have good evidence to support the alternative hypothesis this time. But maybe that's a good thing. That means they didn't find evidence that the mean value is different from 6.35. We hope then the lakes really aren't too acidic. Maybe it's right around 6.35 and not too much above or below. Well, this portion right here in orange, this is just to organize our thoughts with what we're about to say. So coming down below, let's add maybe one more piece of information. Because honestly, this is a tricky situation. I think it's a lot easier to write a conclusion when your p-value is small. Then you could say we have significant evidence that that statement is true. But in this case, let's go and take some extra information for guidance. If you ever have a large p-value, the conclusion goes like this. The study failed to find significant statistical evidence that whatever the statement is in HA is true. So we're now in this portion right here of the p-value problem. This is not a bad one to connect right to this last problem. So let's park it right here as well. Okay, so now we've got lots of guidance to work on, and we're ready for our practical interpretation. So we need a practical interpretation that also captures the context. But if we wrote the value of mu with the context in part A, that really is already taken care of. We'll say here, because we're in this situation, this study failed to find significant statistical evidence to, I'll word it this way, support the claim that now let's read out the value of the parameter mu, the claim that the true average pH of all high mountain lakes in the Southern Alps. There's a lot of context here. So we wrote out mu, and we can now just say it's different from 6.35. Is different from 6.35. So we got it. There's definitely a lot of writing in that last step, but once we get through all of it, this is finally a nice and practical interpretation to capture the whole conclusion. Any questions at all, folks, on getting to this stage? Yeah.
So can you write out the probability of this, like the 2p, and then p is greater than? Like, because this is a two-tailed test, how do you like decide like a sign of them?
Well, pretty much what I was going off of was this table right up here. And the thing that's confusing about this is a great question, is there's a lot of strategies here. So what our author indicates is if t is positive, we take 2 times the area to the right of t. So that's what we did over here, doubled that area. And if t is negative, we could have taken twice this area, but the moment you get a test statistic t, you could put a positive value and symmetrically a negative value. So to really answer your question, it turns out it doesn't actually matter. Let's take another look at this. Let's use negative 1.4451. I'll go second vars to call up the function. Tap 6 for option 6. Now let's use this, negative 1.4451. Oh, well, if I use that value, that's an upper value, right? I put it in the wrong location. If I'm using this tail and I'm doubling that area, I should really start off with negative 10 power 99. And let's delete that one there. Then I'm going up to this cutoff point, negative 1.4451. Degrees of freedom are still 14. We'll get this as an output. Here's the critical step, easy to forget, times 2. And you get the same exact value, it'll round in the same exact way. So the process is actually pretty forgiving. Whatever value you take, just double this area or double that area, and you're in good shape. Does that make sense for that question there? You really can, yeah. I feel like the author was almost too specific on her strategies for calculating the p-value in this case, because there's a lot of ways to do it. In fact, what you could do is calculate this area, calculate that area separately, but what you would get is 0.0852199 and so on, which you would add them both together to get the total area like that. We're using a weird trick to just double this area, but it's only because there is perfect symmetry. This area is identical to this one on the left. Well, other questions about that so far? Or any other questions at the moment? Okay, well, congratulations, folks. That was the last problem of the course, other than the review problems we're about to take a look at. We have quite a few to take a look at. Let me just make sure we've got everything there. And let's save these notes up and go now to the review. So it's been quite an adventure. We started sometime in August, and now here we are. I feel like I put you all through a lot, but I appreciate your hard work to get this to this point. The document I want to start off with is this one right here, Review of Inferential Statistical Methods. This document does include a 12.3 problem hidden somewhere inside there. It's not on the exam, which ends at 12.2, but still will be valuable for telling the methods apart and helpful for the homework as well. But before we look at those problems on the inferential statistical methods, I felt like a good idea would be to stop right here and go all the way back to chapter 1. So imagine this is week 1 or week 2 of the entire course, where we first started talking about information about categorical variables, information about numerical variables. But let's start even before that. One thing we never really defined was what we even meant by inferential statistics. We never put that definition down because we just weren't in a good place to define it. But now we can say inferential statistics is a branch of statistical methods which always involves drawing a conclusion about a population based on a random sample of observations from that population. So that's essentially it. We're trying to, in drawing a conclusion about underlying population, we're trying to say something about the population characteristics, whether they be mu for a population mean or p, a population proportion. When it says based on a random sample of observations, we're using the statistics values like x bar or p hat to make our conclusions. So variable is any characteristic that's going to change from one individual to another in the sample. Data is just a result of making observations. And we'll say a variable is categorical if the observations are categorical responses. That is a horrible definition. I think I typed that out verbatim. Just a tricky thing to define. Categorical data are things like, say, genders, male versus female, or opinions, yes versus no, or categories like successes and failures, which involves p hat all of a sudden. Or it could be things like zip codes. But the best way to tell you have categorical data is whatever the data is, if you can't take the average of it, it's probably categorical. So that includes things like zip codes, telephone numbers, or maybe like eye colors. You can't average a set that says blue, blue, gray, gray is a weird eye color, green, brown, and so on. But if it does make sense to average your data, so maybe heights, time values, distances, you're probably looking at numerical data or quantitative. So that's our review from chapter 1. Any questions at all, folks, with all of that to work there? Okay, what's nice about doing a course like this is it's tough the first time you see these definitions, but if you see them again after all the work we've done, it's almost like your brain is ready. It's turned into a sponge, and you have a lot of traction on all these ideas, taking a look at it a second time. So let's take a look at example 1. It says for categorical data with 2 outcomes. That's the only scenario we really looked at for inferential statistics. There are many, many more, but it was an intro class, so we didn't try to get so crazy. So we kept it to exactly 2. We want to know what is the population characteristic and its associated statistic. We also want to know what is its standard error. And we must use the correct symbol for all of those different answers. Let's start right here. If your data is categorical with 2 outcomes, anyone recall what the population characteristic or parameter would have been? No worries, it's been a while in a certain sense. We've been in chapter 12 for a bit. How about the statistic? Anyone recall what that would be indicated at? What it would look like? No worries if you're not sure. That's kind of the reason that why we need a review. Every single topic that we took a look at, what makes it tough is they were all in its own little world, like its own context. The moment you move out of 12.1 into something new like 12.3, the context changes. But for a final exam, everything is on the table, so we have to now recall quite a bit of information. That's tough to do on the spot, so don't be too worried if you're not sure at the moment. This is only the review, so we can get ready for those new kind of questions on the final. So if you have categorical 2 outcomes and you want a population characteristic, it turns out that thing is P. Weird, because we have things like P for probability, P for p-value, P for proportion, P for percent, it just goes on and on. But in this situation for categorical data, P is going to be equal to the population proportion of successes. Next, we need a statistic that's associated to this thing. Anyone recall what is associated to a P? But what I should actually do here is, we answered that question, so I should indicate this by saying that is the population characteristic. And so no, that thing is always unknown in most common statistical studies. So we need a way to estimate this thing, and the way we do it is with this value, the good old p hat. This one's the sample proportion of successes, and it's calculated by taking number of successes in the sample. Then we divide by the sample size. So that's our statistic, which estimates the population characteristic P. Let's call this the statistic. So we've got two different things. P is the unknown in inferential statistics. P hat is what estimates it. But if you're doing inferential statistics, there's now two different realities we're in. Either you're doing a confidence interval procedure or you're doing a hypothesis test. And in either case, your test statistic, or excuse me, your standard error is going to be dependent on which procedure we're running. So let's break this table down even further. Let's suppose you're doing first a confidence interval. For P. Then on the other side of this table, we'll look at a hypothesis test. For P, and I actually have to be more descriptive here. When I say a hypothesis test for P, if we're going to do the standard error, we need the null hypothesis statement. Let's say a hypothesis test for P where H naught is the statement that P equals the value to be tested. We usually used light green, so let's stick with it, P naught. So we have a couple of different scenarios here. Let's start with the confidence interval. That's the first thing that we did. And this would have been in, let's see if I remember, chapter 9.3. We did a confidence interval for P. Standard error went SE. We threw in P hat just to say which standard error we're talking about. This putting in P hat reminds us it's dealing with categorical data. And it became the square root of P hat times 1 minus P hat divided by the sample size n. So that was our standard error in this problem here. Once we had the standard error, the confidence interval was pretty easy to calculate. It became P hat plus or minus Z star times the standard error of P hat. So that's our full procedure right at that point. Any questions at all, folks, for that standard error? Okay. Now, what's really rude about chapter 9.3 is we've become awfully familiar with that. We calculated it a couple dozen times in getting through chapter 9. But when you go to, say, chapter 10, section 5, I'll just call it chapter 10.5, the formula changes on us, and that can be kind of a dizzying experience all of a sudden. It turns into standard error of P hat equals the square root. We still have the sample size n down below, but the numerator is now different. Anyone recall what goes up in here for the hypothesis test? Good call, absolutely. The hypothesis test is incredibly different than the confidence interval in the sense that if we assume that this is true, we don't need the estimator. We need the true value. P is P naught if the null is true. So we throw in exactly like you said, P naught times 1 minus P naught. I just want to fix some of that penmanship here. That looked kind of funny. Divide by n, all square rooted. So if we're doing a hypothesis test, that would be our standard error. And we would calculate one extra thing after that. We would need a test statistic. Problem didn't ask for a test statistic, but what the heck, let's throw it on there and show what it would look like. In a hypothesis test, the test statistic is a z-test statistic. This tells us we're going to use the normal distribution when we go to get our p-value, but everything about the left-tailed test, right-tailed test, and the two-tailed test, all of those diagrams are exactly the same. We're just converting to the normal distribution. The formula is different for z compared to t. This one is going to be, we take in the numerator, the statistic p hat. We need to know how far is it away from the null hypothesis value, P naught. So we're seeing how far away our data is from the null hypothesis claim in terms of standard deviations. So if you divide by standard error P hat, this calculates how far away our data is from the null hypothesis statement in terms of approximated standard deviations, the standard error. So that's the full process. And if I was trying to tell apart what's going on with categorical data, I think this is just about as much as you could say. These are the main things to keep separate in our mind: the confidence interval versus the hypothesis test. But any other questions or comments, folks, or things you'd want to include here? Okay, so far, there's two situations. If you know your data is categorical, then you're either using this information on the left or this information on the right. And usually you can tell if it's going to be a confidence interval or a hypothesis test, because one of the parts will ask you to state hypotheses. That plants you firmly in this place. But now if your data is numerical, everything kind of changes around. So let's start this all over again for numerical data. We'll start off. We need a population characteristic. For numerical data, anyone recall what that one would be? That one would be the associated statistic. So you're absolutely on the right track. So let's put down that one first. The associated statistic will be X bar, which is equal to the sample mean. And, sometimes it's not a bad idea to put a possessive here. It's the sample's mean changes your point of view, and it reminds you that X bar is only talking about the random data that came from the sample, nothing else. So this is the statistic. This one is always the known value. It's going to estimate something. And we need to say, what is this thing and what is its symbol? Anyone recall what would be the population characteristic or the parameter associated to X bar? That one is mu, absolutely. So we'll throw down mu is the populations. I'll just say population mean. It's kind of strange in a certain sense, because if I have a problem like this where there's no context, the best I can say is population mean, or maybe true mean or average or something like that. But if we're doing a real problem and we have to describe this, we have to say the mean of what exactly, and we also have to say what is the population when we're doing this. So that's why we usually say things along the lines of all high mountain lakes, the mean pH, for example. So we have our population characteristic here. And just like before, we can split this into two different kind of scenarios. Either you're doing a confidence interval or you're doing a hypothesis test. So let's split apart in just like before. So this will be a confidence interval. And it's a confidence interval for mu. Mu is the unknown, and the whole purpose here is to estimate it, versus a hypothesis test. For mu, like before, we have to specify the null hypothesis. So let's say where H naught is a statement that the population mean, the thing that's unknown, is actually equal to some quantity. We'll designate it as a mu naught when we go to write these in formulas. So those are the two different situations, and we want the standard error in either case. This is kind of forgiving for this type of situation. It turns out the standard error does not depend on what method you're using, confidence interval versus hypothesis test. In both cases, it's SE for standard error. We say of X bar to say which one we're referring to, what kind of data is it. And we'll put in S, the sample's standard deviation, divide by the square root of the sample size n. And same exact thing over here. So it really is kind of unusual that in the last situation, standard error changed, and it changed substantially from this point of view. It was only because of the parameter value going inside here, giving us a p hat. But over here, it was sigma over root n. We estimated with S, a totally different statistic from X bar. That's why it comes out as the same in both of these situations here. So we've got the standard error. And let's add a little bit more, just because, we're looking at it. Let's say what else you would have to do if you're finishing out this problem. the confidence interval procedure turns into X bar plus or minus T star times that standard error of X bar, where T star is based on DF. This just stands for degrees of freedom, which is equal to n minus 1. So we have to find that critical value T star based off n minus 1. This, again, as a reminder, I will give the T star value on the final exam, since some calculators don't actually have the function to calculate it. Now over here, we don't need a T star value, we need a test statistic instead. So let's indicate this on the right-hand side. If we're doing a hypothesis test, then the test statistic this one is going to be T is T equals, we start off by observing whatever the value of the statistic is, and we want to know how compatible is that with the null hypothesis. So we form the difference of X bar minus mu naught. Notice this is exactly the same as what we did above, where we went P hat minus P naught. Then down below, we need to figure out how far is that distance in terms of approximated standard deviations, which we refer to as standard error. So that's our test statistic in this situation. And that's pretty much our whole rundown. So if we can determine if the data is categorical or numeric, we'll know which set of formulas we're dealing with. And if we indicate right away, are we doing a confidence interval or are we doing a hypothesis test, they'll designate one specific set of formulas. But the unfortunate thing is there's 4 possibilities, right? This one, this one, this one, and this one. Let me put down a reminder. This is not on the final. We'll still work with it for practice for the homework, but this one is on the final. But that one's not too bad. I think when we finished out the section 12.2 on that, we ended up doing it faster than intended because there's not a whole lot to do on these. They're pretty fast problems, actually. So now our goal is take a look at 4 randomly generated problems, and they're sorted in a random way, decide the method, and execute the method as well. So here's our first one to start off. When we read through this problem, first thing we have to decide, is the data categorical or is the data numeric? Let's read through it and see what's going on. Example 2 say, most like it hot, is the title of a press release issued by the Pew Research Center, March 18, 2009. The press release states that by an overwhelming margin, Americans want to live in a sunny place. I agree with them as an Idahoan. The statement is based on data from a nationally representative sample of 2,260 adult Americans. Well, so far, I'm not completely certain of the data, just reading that far. But if we have a sample size, it's always a good idea to just drop that down. And it's 2260. Even if, let's say, you're taking the final exam and maybe you have everything down except a last problem. You just ran out of time. If you put this on the last problem, that is still partial credit because you're telling me something about the problem which you need to solve it down below. Anything you put on the paper which indicates to me understanding about the problem is worth partial credit. And this kind of summary stuff, that's probably the most important thing you could do when you're taking a look at a brand new problem. Translate given information into our notation. So next paragraph says, of those surveyed, 1,288 indicated they would prefer to live in a hot climate rather than a cold climate. I don't know what to do with that. That's not an average. That's not a standard deviation. It's not a sample size. What would you all call that when you saw that value there? It's almost kind of hard to say at the moment, right? Well, let's pause on that. Let me highlight it. And we'll go to the next statement. It says next, suppose that you want to determine if there's convincing evidence that a majority of all adult Americans prefer a hot climate over a cold climate. That's a suspicious word right there. Sorry, that was hard to say as well. A majority of all. When they say a majority of all, let's take that word here. They're saying more than 50%. So that's an interesting statement right there. Again, not too sure what to do with it just yet, but this is the moment of truth. Does this look like we have categorical data or numerical data? I totally agree. This looks very categorical. And this highlighted comment here, that looks like it's just the number of successes in the problem. We have a percentage, and there's nowhere a unit tied together with a number like inches or pH values or anything at all like that. Looks like we're in the land of categorical. So let's say that right away. These data are categorical. And if we look through the problem, notice it says state the null and alternative hypothesis. So now we know if we were to turn up to the notes just for a moment, we're doing this problem right here. We have categorical data running through a hypothesis test. Okay, so let's see what else we can do. Since we have a sample size, and since these are the number of successes, we can actually calculate p hat right here now. P hat is going to be 1288 divided by 2260. So we have a sample proportion of successes. Because we put p hat right here, that means when we go to clearly define the unknown population characteristic, we'll be using p rather than mu. P is always conflated with p hat, and p is just estimating this unknown right over here. But we have to say, what is p exactly? Let's say p equals, we can't say mean or average in this problem because those designations are only for numerical data. We have to either say proportion or percent. I'll go with proportion. P equals the true population proportion of Americans that prefer, I'll just say warmer weather or climate. So we have a parameter. This is the unknown that we're going to test in this problem. It says state the null alternative and choose a level of significance. So we'll have a H naught and HA. I always use this color for the significance level, so let's keep it the same as an alpha. Because we have a parameter P in our null hypothesis, we're testing P. So P goes here, same in the alternative. The null is always a direct equal, but over here, this one has a directionality, sometimes two directions if it's a two-tailed test. And now this is where it can be a little bit confusing. Anyone see what should go right here? Absolutely. When they asked us this question right here, or it's more of a demand, suppose you want to determine if there's convincing evidence that more than there, we'll have a greater than symbol. But notice how tricky this one was. This one would be a bad exam question, in my opinion, because the statement a majority of all, we have to unpack to mean they meant more than. So they mean a right tail test, a greater than goes here. The value of 50% turns into the value to be tested. So that's P naught at 0.50. So 0.50 will go here and here, both in the null and in the alternative hypothesis. So that gets us through the hardest part, in my opinion, determining the population characteristics and setting the hypotheses. Conditions are not so bad. First, let's take a look at what they said about the sample. They said this statement is based on data from a nationally representative sample of 2,260 adult Americans. Though our textbook is kind of odd, a lot of the studies say representative sample. I've started to notice that. In other textbooks, they get studies that say they were actual simple random samples. But let's go with what we know so far. The sample is representative of all Americans. Definitely doesn't sound like it was random, so that's a little bit of a problem. Question first up here. Oh, geez, I even wrote it and never actually tied it off. Thanks for spotting that. Let's back up from there. Our conditions are half done, but really, unless we have alpha, we shouldn't even do any of the test. We need to know the level of evidence. And this time it's pretty much all up to us. Any volunteers for a decent level of significance on this one? Middle's not a bad one. Let's go with that, a 0.05. And again, we could turn this problem into a pretty enormous one by writing down what is a type 1 error using the context, what is a type 2 error using the context. Those problems are actually pretty difficult. Yeah, go ahead.
Like on that train of thought, on the exam, is that something that like we should be prepared to do, is take the significance level based on that, like what error returns they reduce?
Yes, absolutely. But what I won't ask you to do on the exam is I won't make you actually write down type 1 error, type 2 error using the context, because I feel like that on its own is a pretty enormous problem. Here, put something that seems reasonable and you'll be in good shape. And because that's a potential exam problem, let's put something else here. There are some values that just don't work. And we'll say here, typical values range from a 0.10. It's almost, I wouldn't say impossible, but it would be extremely irregular to have a significance level alpha larger than that. That's pretty bizarre. So they range from as large as 0.10 to a 0.01. Sometimes people do make this pretty small. If they decide that, say, a type 1 error is dangerous, this could be a 0.001, or maybe you're designing a new plane and you have a statement that has to do with something from the physics, the aerodynamics, things have to work out just right. That might be set to a 0.0001 and so on. So this can get very, very small, but almost never is larger than a 0.10. That would be bizarre and pretty questionable statistics at that point. So if you have to pick your significance level alpha, I'd say anything in this range is pretty good. And like you were saying, picking something in the middle is pretty safe. You're balancing type 1 against type 2 errors. So it becomes kind of an exam question of knowing what is a good value to place and what would be not a great value as well. Other questions about that so far? Yeah.
So, the errors like numbered, thinking about like hypothetically, like what significance level to pick, you can tell that like from just pulling out of the context and like hypotheticals from which errors, like what error is going to cause what to happen, right?
Sure, you could write down what is a type 1 error, was a type 2 error, and that would direct you much better at what alpha really should be in the problem. But like I said, that's like a completely different exam question. If you put down a 0.05, that would be okay, even if you didn't consider too hard type 1 error versus type 2. But am I answering your question about that on alpha?
I think so, yeah.
Okay.
I just want to make sure that like, if I need to be that I'm prepared to be able to like break down, what the errors mean, so that I can take a significance level, like I need to show that one.
You do not need to show that, no. Yeah, and that was a comment I was about to make, but I think I got sidelined a little bit. On the actual real exam, I'm not going to ask these questions over here from section, let's see, where would that have been? 10.2. These were tough problems if you remember correctly, where we had to take these things, write down what is a type 1 error, what is a type 2 error. But the actual big takeaway from all this was the only reason we really did this was because we want to specify the role that, sorry, it's going too far. We want to specify the role that alpha is actually taking every time we put down a significance level alpha, and why it's so vital on comparing the p-value against alpha itself. So alpha is the probability of a type 1 error, and the larger your alpha is, smaller the value of beta is going to be, and that's the probability of a type 2 error there. Other questions about that so far? Okay, so yeah, this could be definitely a plausible question where we have to really put down our significance level alpha. it's gonna go potentially one way or another. Not every problem did that. But a 0.05 is a pretty good choice for this one. Other questions or comments so far? Okay, looks like this is a good stopping point for us, folks. When we come back, we'll finish the conditions and just keep on running through this document.
I know I only turned 90 and probably should be a straight line, but
Oh, no worries at all.
um,
Awesome, thanks.
is the final gonna be like for my when I did my psychology final, it has like this section for each page, so like you knew like where to look for your notes. I don't know if that makes sense, but like
It does make sense, yeah.
Okay.
So on the final, it's gonna look more like, say, these problems. It won't say what chapter or section it's out of,
Mhm.
but what I'm not doing on the final is I'm not scrambling the problems. So it will
Okay.
be in the order
So
we did the course.
Okay, perfect, thank you.
Yep, you bet.
What's the scenario where, like, when we're testing it's 30 instead of 10?
Oh, you're thinking of numerical data. So if we're dealing with numerical data, let's pull up those notes. Then our central limit theorem changes quite a lot in that situation. And here it is. That's where that rule of thumb comes from. If the sample size is 30 or greater, now I have a huge disclaimer here. For a lot of studies, that's pretty safe. And we'll find out that for our problems, that's probably going to be the case. But the more statistics you take, the more we're gonna find that there are problems where 30 is just not enough. It does depend on how badly the data is skewed. So think of this as a rule of thumb that works okay for our class, but
Yeah.
the more statistics we take, the more we're realizing that falls apart sometimes.
So like in that chart that you made like on the review page,
Mhm.
where does this kind of like fall into that?
This would be for checking the conditions.
Okay, for like numerical data, like any numerical data? then?
Yeah, this is actually the right condition for both the confidence interval and the hypothesis test.
Okay, so like when it's the categorical, then it's always gonna be this, and when it's numerical, whether it's like for checking conditions for like, an interval or testing the hypothesis, it's always the 30.
Yep, exactly.